We are going to talk about simplex algorithm again, but this time it is dual simplex. So let's start. So in the usual simplex algorithm, we call it primal simplex. We start with a problem, let's say maximization, the Dakota problem here. We start by looking at the row 0 and it has negative coefficient. So we perform the simplex algorithm until we reach the optimal table in which we do not have any negative coefficient in row 0. Then we have reached the optimal solution. So we can say that for the primal simplex, we start with the solution that is not dual feasible. Why is it not dual feasible? Because it has negative coefficient in the row 0. The negative coefficient here means that if you use these basic variables, S1, S2, S3 for this solution, find the corresponding dual solution using CBVB inverse, then you will get solutions with E1 equals minus 60, E2 equals minus 30, E3 equals minus 20 in the dual problem. And that is not feasible in the dual, because in the dual problem, the excess variables must be non-negative. So we start with the solution that is not dual feasible. However, it is primal feasible. It is primal feasible because all the right-hand side is non-negative. Okay, so that's how we start the simplex algorithm for the primal problem or the primal simplex. And then while we are doing the simplex algorithm, what we want to do is that we are going to reach the dual feasibility, which means that there is no negative coefficient in row 0, while at the same time we maintain primal feasibility. We keep the right-hand side non-negative. Actually, this is why we do the ratio test in the simplex, and then we always pick the smallest. We try to maintain primal feasibility. In dual simplex, we do the other way. So we start with a solution that is dual feasible, which means that in the row 0, there is no negative coefficient for maximization problem. However, we do have a negative right-hand side. So this solution is not feasible in the primal because we have a negative right-hand side. We will perform the dual simplex such that the dual feasibility is maintained. We do not have negative coefficient in the row 0, but then we have reached the primal feasibility. We do not have a non-negative right-hand side. So you notice here the key now for dual simplex is in the right-hand side. We have negative right-hand side, and then we perform the algorithm until we do not have negative right-hand side anymore. Here are the 3 steps in the dual simplex. I will highlight the key of each step. For the first step, the key is checking if there is any right-hand side that is negative. If there is negative right-hand side, we're going to step 2. If there is no negative right-hand side, then we have reached the optimal solution. So if there is a negative right-hand side, we go to step 2. And in step 2, first we need to determine the leaving variable. Then we perform ratio test such that we know which variable becomes the entering variable. Then we will perform error as usual to make the entering variable enter the basis and then put the leaving variable out from the basis. Once we have done that, we go to step 3 and decide whether the problem is infeasible or we need to do more iteration. So going back to step 1, see if there is any negative right-hand side, go to step 2, and so on. So these are the 3 steps in dual simplex. Looks like it's the steps are long and so on, but you will see later that it is quite simple actually. We are going to apply dual simplex to these 3 problems. First, finding the new optimal solution after a constraint is added to an LP. If you recall, this is the change 6 in the 6 changes that we talk about in week 10. So let's start with this. When we have obtained an optimal solution and then we add a constraint, one of the following cases happens. Case 1, the current optimal solution satisfies the new constraint. Second, the current optimal solution does not satisfy the constraint, but we still have a feasible solution. And the third one, the current solution does not satisfy the constraint such that the LP now has no feasible solution. Let's start by looking at the first case. In the first case, suppose we add this constraint to the Dakota problem, x1 plus x2 plus x3 less than or equal to 11. Now here is the optimal solution for the Dakota problem before we add the constraint. So this is the old optimal solution. When you add a constraint and then you have been given the old optimal table, the simplest thing you can do is check whether the current optimal solution satisfies this constraint or not. So plug in the value x1 equals 2, x2 equals 0 because it is a non-basic variable, x3 equals 8, so 2 plus 0 plus 8 is indeed less than or equals to 11. It means that the current optimal solution satisfies the new constraint such that the current basic variables, they remain optimal. In this case, when we add a new constraint, it does not affect the original optimal solution. Now let's see the second case where when we add the new constraint, the current optimal solution does not satisfy the new constraint. Let's say we have a constraint saying that x2 must be greater than or equal to 1. In the old optimal solution, we see that x2 equals 0 because it is a non-basic variable. So it is clear that the current optimal solution does not satisfy the new constraint. So what we need to do is the following. Convert this constraint into standard form. So because the sign is greater than or equal to, we will put minus excess variable. And then we multiply the entire constraint by minus 1. So the excess variable E4 becomes basic variable. Then we append that to the old optimal table. So here's the result to make it clear about what I just said. Okay, so we have minus x2 plus E4 equal minus 1. Okay, this becomes minus because here we multiply the entire constraint by minus 1. So originally it was x2 minus E4 equals 1. After the multiplication becomes minus x2 plus E4 equals minus 1. The purpose is to make E4 a basic variable. So you can see that E4 here in the canonical form, so E4 becomes basic variable. So here's the new table after we append the new constraint to the optimal table. But remember that before you append the constraint, you need to convert it to standard form, multiply by minus 1, such that this row has the basic variable E4 equals minus 1. And then make sure all the basic variables are correct. So what I mean here is that you need to check, okay, S1 is in the canonical form, so S1 is the basic variable. X3 is also in the canonical form, basic variable. X1 is also in canonical form, so it is a basic variable. And E4 is also in canonical form. Remember that canonical means coefficient is 1. It is plus 1, not minus 1. So plus 1 in this row, and then 0 in all other row in that column. So we have ensured that all the basic variables in this table are correct. Now we see that we have a negative right-hand side, so we need dual simplex. So in the first step of dual simplex, we check is there any right-hand side that is negative. Yes, we do have a right-hand side that is negative, so we go to step 2. Step 2, we start by choosing the leaving variable, which is the most negative basic variable. So here in this case, the most negative basic variable is E4. So E4 will become the leaving variable. Now perform ratio test for this row. So you look at the row where you have the leaving variable, and then you perform the ratio test for all variable that has a negative coefficient. So here in this row, x2 has a negative coefficient, and here in this row is just x2. So you perform the ratio test for x2. The ratio test is the coefficient of xj. In our case, this is x2. So the coefficient of x2 in row 0, 5, divided by the coefficient of xj in the pivot row. This is our pivot row. The coefficient of is minus 1. So the ratio is 5 divided by minus 1, and take the absolute value. So the ratio is 5. In this case, we only have one ratio. In the case where we have more than one ratio, we pick the smallest, the absolute value, and then the smallest among all absolute values. Here we only have one ratio, so there's no other choice. We pick this intersection between the leaving variable and the entering variable as the pivot position, which means that we need to perform elementary row operation such that this position here, the coefficient becomes 1, and then in all other position in that column, the coefficient becomes 0. So we perform error, and then we get this table. So when we look at this table, we see that all the right-hand side, they are already non-negative, which means that we have obtained the optimal solution with respect to the new constraint that we add to the problem. Now in the third case, we are going to add a constraint, but when we add that constraint, the linear programming problem becomes infeasible. So here we are adding a constraint saying that x1 plus x2 must be greater than or equal to 12. The old optimal solution does not satisfy this new constraint because x1 equals 2 and x2 equals 0 because it is a non-basic variable. So what we need to do is, same as before, we are going to append the new constraint to the old optimal table. And here are the steps. Convert this constraint into standard form. Because the sign is greater than or equal to, we put minus E4, minus excess for the fourth constraint. We multiply that constraint by minus 1, so now E4 becomes basic variable. Then we append that to the optimal table. So this is the result of the constraint after we add the excess variable and then multiply it with minus 1 for the entire constraint. But before we continue, we need to check, are the basic variables correct or not? S1 is correct because it is in a canonical form. X3 is correct, it is also canonical form. E4 is also correct, this is in a canonical form. But if you notice X1, it is not in a canonical form. So X1 in this table, it is not a correct basic variable yet. We are going to perform the correction before we continue to the dual simplex algorithm. So in the old optimal table, x1 is a basic variable. So in our new table, after we append the constraint, x1 must also be the basic variable. So how can we do the correction from here to there? What we want is to make the column of x1 becomes canonical. So only at this position the coefficient is 1, and at other position in the column it equals 0. We perform arrow or elementary row operation. So we obtain the new row 4 equals the old row 4 plus row 3. So old row 4 plus the row 3, we will obtain the new row 4. Now you can see that this table at the bottom, it has all the correct basic variables, which means that the basic variables are all in the canonical form. Now we proceed to the dual simplex. We have a negative right-hand side, and then we pick the most negative basic variable at the right-hand side to become the leaving variable. Here it is E4 as the leaving variable. Then we look at this row and look at all variables that has a negative coefficient. Here we have S2 with the coefficient minus 0.5. So we perform the ratio test, 10 divided by minus 0.5, and then take the absolute value. So we have the ratio equals 20. Because we only have one ratio, so S2 becomes the entering variable. If we have more than one ratios, we always pick the smallest. Okay. Now S2 becomes entering variable, and this position becomes the pivot. It means that in the next table, this position must be 1, and all other coefficients in that column must become 0. So we perform arrow elementary row operation such that we get this new table. In the new table, we still have a negative right-hand side. So again, we pick the one that is most negative to leave the basis. Here it is x3 is the most negative basic variable, minus 32. And then this is the pivot row. And then again, we notice each variable in that row that has a negative coefficient. Here we only have x2 with the coefficient minus 1. We perform ratio test, 10 divided by minus 1, take the absolute value, so the ratio equals 10. Again, because we only have one variable in the pivot row that has the ratio, so x2 becomes the entering variable, and this position becomes the pivot. So in the new table, that position must have the coefficient of plus 1, and all other variables must have the coefficient 0. We perform arrow to achieve that. Okay, and then from the new table, we still have a right-hand side that is negative. However, if you look at this pivot row, there is no negative coefficient for any variable. It means that in step 3 we conclude that this problem becomes infeasible after we add the new constraint. So that was the first use of the dual simplex, and then we are going to talk about the next two uses in the next video. Here's a question regarding case 3. In case 3, we add this constraint to the Dakota problem, and then we perform dual simplex such that we arrive at the table that looks like this. The statement is, this is a sign of infeasibility. It is case 3 because the z value is negative. Is this statement true or false? I will give you the pause on the video, and then I will return after the pause with the answer. The answer is false. The correct reason of why this table shows infeasibility is because we see that the right hand side is negative. However, the left hand side, they all have positive coefficients. And then we know from the sign restriction that the value of the variable itself must be non-negative. So the value of the variable must be non-negative. The coefficients, they are all non-negative, but then the right-hand side becomes negative. So it cannot happen, right? On the left, everything is non-negative, but the result on the right becomes negative. So that's why this is the sign of infeasibility. It's not because of the z value. Okay, so that's the end of this video, and then in the next one we're going to talk about the other two uses of the dual simplex. So see you on the next one. Thank you.